Welcome back. In the previous video, we designed a full RAG ingestion pipeline, and one of the most important decisions we made was how we chunk documents. So we scanned the cleaned text line by line and treated short capitalized lines as section headings and grouped the lines underneath of each heading into a chunk. Each chunk includes its heading plus the body underneath it. We attach metadata like document ID, a content hash, and a deterministic chunk ID. This gave us semantically meaningful chunks which are stored here. And we have enough identity to safely update or re-index document in ingestion pipeline. So when we update a document, the system knew exactly which chunks had changed and which ones stayed the same. That's why when we modified the document, the vector database stayed clean. In this video, I want to zoom on that exact design choice. I'm going to show you what breaks when chunk IDs are designed incorrectly and why content-based chunk identity is the foundation of safe, idempotent, and consistent RAG ingestion. First, we go through manifest and vector index file. Your manifest file is your ingestion memory. It records what you previously indexed, so the next run can correctly decide what to skip, update, delete instead of just doing guesswork. So there are some important piece of information that a manifest file usually store. There should be a document content hash. That is the hash of cleaned document content. If this hash hasn't changed, we can safely skip rechunking, re-embedding, and re-indexing. Another piece of information is chunk IDs. This is a list of chunk IDs currently present in the vector index for this document. This is what makes deletes and updates safe. If a document changes, we delete these chunks and then upsert the new ones. Next field is updated at UTC. This is just a timestamp so we can trace when the pipeline last touched this document. In production, the manifest doesn't live as a local file. It lives in a durable metadata store like a database. For example, on AWS, you can store it in a DynamoDB or RDS. For larger document collections, this lets the ingestion pipeline process only what changed, safely handle updates and deletes, and run in parallel without corruption of the vector index. The manifest becomes a control plane that keeps the vector database correct as a corpus scale. Now let's talk about vector databases. So I'm using a standalone file, which is a simple JSON file here, so we can easily see exactly what's happening and what's changed. Conceptually, this file represents the final state of vector index after ingestion. Each entry corresponds to a chunk that is currently searchable. So you can see the IDs would match to the IDs here. This starts with 26cc and the first one is here. So in real system, this would live in something like OpenSearch, Pinecone, or any other vector store, but the semantics are identical. Okay, let's look at the structure of this file. At the top level, we have chunks. Then we store everything by chunk ID, which is the primary key of the vector database. That's because the retrieval happens at chunk level, not document level. So we have to have a correct identifier of the chunk itself. Then we have document ID. We store it as a metadata. This lets us group chunks by documents for deletion, filtering, or permissions. In real vector databases, this would be metadata attached to the vector. Then comes embeddings. This is an array. This represents the vector of the chunk. In this demo, it's a fake embedding, so the pipeline is reproducible, but in production, this would be something generated by a real embedding model. Then comes embedding model and version. These fields are critical in real systems because embeddings are derived from data. If the model or the version is changed, the vector becomes stale. So tracing this explicitly lets us re-embed safely later. So the manifest tells us what should exist and the vector index shows us what actually exists after ingestion. Now we understand those two files. Let's put them under stress. I'm going to run the same ingestion pipeline that we saw in the previous video 3 times, changing only how chunk IDs are generated, and we'll watch how the manifest and vector index behave in each case. This will make it very clear why some designs silently corrupt your vector databases and why others stays correct. So let's dive in. In this demo, we have two input documents. One is policy refunds.txt and the second one is security policy. This is the one that I will edit to show the chunk IDs changing, and this is the one that remain unchanged. Let's start with the most common chunk ID design I see in real systems. So we take the document ID and we append a chunk index and call it a day. So I'm going to comment this line, which is our real document chunker, and I'm going to paste this code here, okay, so you can see that we are calculating the chunk index and then appending that index to the document ID. And that's what our chunk ID is. At first glance, this feels deterministic. The IDs look stable, they are readable, and they are unique per document. Then we are going to run the pipeline and see what it insert into our manifest file and vector database. We go to our job and hit launch run, and it started the pipeline: extract, clean, embed, index, and the summary, and looks like the pipeline is successful. Now we go back to the VS Code and let's go to our vector index JSON file. We can see that the chunk IDs are policy refunds 1, 2, 0, 1, 2, and then security policy, which was our second document, has another 3 sections. So there should be 0, 1, 2. So there are total 6 chunks here. And if we go back to the manifest, we can see the chunks IDs are matching with the chunks ID in the vector index. So everything looks fine until now. Then we are going to add another paragraph at the top of policy refunds.txt, and we are going to call it something else. So let's say we say risk policy, and we just replace the keyword refund with risk and save it. And I'm going to Dagster UI again to rerun the pipeline. And okay, let's go back to our job and hit launch run again and wait for it to complete. All right, it's successful. And now watch closely. By inserting a paragraph near the top, I did not change the meaning of most of the documents, but I shifted the chunk boundaries. You can see that in the policy document we had 0, 1, 2, but now that we added another one at the top, it becomes 0, 1, 2, 3. But because the chunk IDs are tied to the position, every chunk after that point got a new identity. The system can no longer tell which chunks are actually the same. The old vector don't get deleted, only the new one which is policy refund 3 gets added, and the old one remains the same with the old data. This is how you end up with stale context in your vector database, even though your ingestion job succeeded. So index-based IDs looks fine until document evolves, which is exactly we try another approach people usually use to fix this problem. The approach is random UUID chunk IDs. So we go back to the file and we are going to bring the original text document to its original form. Then we go back to our definition file. Now instead of index-based chunking, we are going to replace it with UUID. Okay, so we have to import UUID. Now we are going back to the Dagster UI and rerun the pipeline. Let's go back to the job and launch the run and wait for it to complete. So extract, clean, embed. Oh yeah, so looks like it's successful again. We can see that we have 3 chunks. So far everything looks good. Please note the chunk ID. We have 3 chunks for the policy refunds document and 3 chunks for security policy, and we have corresponding embeddings in the vector index file. So let's rerun this pipeline and see the output. I'm going back to the job and launching another run in the launchpad and wait for it to complete. After running the ingestion pipeline the second time, notice something important, that we still have 3 chunks for policy refund document and 3 chunks for security policy, which looks all good at first glance. But look at the IDs. The IDs are completely different, which means that every chunk now has a completely new identity. Every run generates a new UUID, which is new set of chunk IDs. The system cannot tell whether these chunks already existed or not. Any delete or update now relies on assumptions instead of facts. The system has no stable identity to compare against, so it can never delete or replace anything. So now this tells us that index-based IDs break when documents are changed, but UUID-based chunk IDs break on reruns. Now we move to the third approach, which is content hash-based chunk IDs. We are going back to the definitions file and we are going to comment the UUID line, and we are going to produce chunk IDs using the chunk text plus doc ID, which is a content hash, and we are hashing the content using SHA-256. So let's run the ingestion pipeline. Going back to the job again and launching one more run. Once this is done, we go back to the Visual Studio Code and see the manifest and vector index file. So it's successful. With content hash chunk ID, we are driving the chunk identity from the meaning. If 2 chunks have the same content, they get the same ID. If the content changes, the ID changes. And now we go to manifest file and we can see that the policy refund has 3 chunks and the security policy has 3 chunks, and we are going to save the IDs. And now I'm going to update the content. Maybe I'm going to add another line here, and I'm also going to add another section to the policy refund file. Policy refund document. And I'm gonna call it risk policy, and I'm going to add some random lines here and going to rerun the pipeline again. Run the ingestion pipeline the second time. Now we had 4 sections in this document. That means we should have 4 chunks, and we updated this chunk and we also added a new one, and these 2 remain unchanged. So in the manifest file we can see that now the policy refund document has 4 chunks. You can compare the IDs with the previous IDs. You can see A4 and B27C, these remain unchanged, and we have a new chunk plus another chunk where we changed the content. So we can go back to the vector index and we have a new one where the content was updated. So we should have the corresponding embedding in the vector index file. So you can see that only the chunk whose content changed receive a new ID. All unchanged chunks kept their identity. Chunk identity must be derived from content, not position. I can rerun this pipeline hundreds of times. The final state would always remain the same. That's idempotency, and that's not negotiable in production, because we cannot compromise our vector databases, because that means the whole content is corrupted. So let's recap what we actually did in this video. We took the chunking logic we designed in the previous video and we zoomed in on one specific decision, which is how chunk identity is defined. We looked at 3 different chunk ID designs. First, we tied the chunk identity to a position. That worked until the document changed. As soon as we added one more document at the top of the text file, everything broke. The second method we used was random UUIDs. That looked stable on the surface, but the system lost all ability to reason about updates or deletes, because as soon as we ran the pipeline, it regenerated the UUIDs that were the chunk IDs, and it did not know which one to delete, which ones are old, which ones are new. So finally, we derived the chunk identity from content itself, from the exact text we embed. Once the identity was tied to meaning instead of position or random UUID, updates became precise, deletes became safe, and reruns became idempotent. In the last video, we proved that ingestion pipelines works and how important is it to design them carefully. And in this video, we showed why it works and how easy it is to break if chunk identity is wrong. In the next video, we will move one layer up and talk about metadata, and we also talk about some frameworks to design the RAG pipelines. If this helped you understand chunking better, please like and subscribe, and I'll see you in the next video.